right, so what I would say about today is, at least for my, we're going to talk kind of very broadly under the guise of graphing. So everything we're going to talk, at least everything I'm going to start talking about, maybe we'll switch gears halfway through, but at least for now, really all the things I'm going to say, most of the things I'm going to say have to do with graphing. Let's start off by talking about a couple things we talked about at the end of last class. I'll remind you of a few theorems that you might have seen already. Well, I guess I'll tell you about a few theorems. So the extreme value theorem just says that a function attains its maximum and minimum on a closed interval if it's continuous. So if f of x is continuous on a closed interval AB, then the function f of x attains an absolute maximum and an absolute minimum. And furthermore, they occur at either critical points of the function or at the endpoints. Those are the only places where it can occur. So maybe you have a function that looks like this on some closed interval, where the minimum is occurring right there, and the maximum is occurring right here at a critical point. Or maybe you have something that's always increasing like that, so the minimum is at the left endpoint, and the maximum is at the right endpoint. Or maybe you have something where the absolute maximum don't occur at the endpoints at all. Maybe you have something that looks like this, where the minimum is at some critical point, and the absolute maximum is at some critical point. As long as the function is continuous on a closed interval, you have to get an absolute maximum and absolute minimum. And then kind of conversely, if your function is not on a closed interval, for example, if you think about the function y equal to x squared, which looks like this, just on the entire natural domain of that function, it definitely does have an absolute minimum at the origin. It definitely does not have an absolute maximum, right? It just gets larger and larger and larger as you go left or right. So this does not have an absolute max. And again, we shouldn't necessarily have one because it's not a continuous function on a closed interval. Similarly, a function that's not continuous, something I'm just going to graph something like something that looks like this. Ooh, yeah. Oh, this is going to be good. Like this one here. Let me make it a little bit better. So if I have something that looked like this, then like that. And I'll label my points here. So that's going to be like 2. That's going to be 5, 3, 4. This function is definitely, the way I've drawn it is discontinuous. And let me zoom in on it a bit just so you can see it a little bit better there. Function's for sure discontinuous, and it doesn't have an absolute maximum or let me close this one off here actually, since it's so at least it's on a closed interval. So this function, the way I've drawn it, does have an absolute minimum because I just filled in that point there, and the absolute minimum would be a minimum. What is the way I've drawn this? If you can read it well, what is the minimum value that I've tried to draw? So it would occur at 6, but the value would be the y value, which is 1. So you can say the minimum is at 6, 1, or you can say the minimum value occurs at x equals 6 with a value of y equals 1. On the other hand, there is no maximum value here. Well, it's not even that it's undefined. This function is, so I will point out the function I've drawn here, f of x is defined everywhere on the closed interval from wherever I'm starting here. Let's say that's 1 as well, on the interval from 1 to 6. There's no place I've drawn where it's undefined. Specifically looking at 4, f of 4 is equal to 3. And certainly a function passes the vertical line test. But there's no maximum because of the discontinuity here. You might be thinking to yourself, I'm pretty sure there's a maximum there and it's 5. But there's not. I might ask you, we don't actually get to 5. So what's the biggest value we get? I get bigger than 3, right? Because like up here, like I'm like 4.1, 4.2, 4.3, 4.4. I'm getting closer and closer and closer and closer and closer to 5, but my y values never get to 5. And the problem here is there isn't a maximum if we don't actually get to 5, because you can't say the maximum is like 4.999. When are those 9's going to stop? Never. So there isn't an absolute maximum here. And if you said the maximum was 4.9 forever, I would say it's not, because that number is actually equal to 5. It's kind of weird, but it's true. Okay, so that's the extreme value theorem, and we've definitely been using it already, right? We definitely talked about how you find the absolute maximum, absolute minimum by finding the critical points and then testing testing the endpoints and the critical points to see if you have which one's the biggest and which one's the smallest. So just to give you another example. Oh yeah, because I like this example. Let's say it's a good example. Let's look at, for example, I'm sorry, let me zoom back out to regular viewing scale here. All right. Oh, it's hard to. I wish I had like, I wish this can't, I mean, this is an inexpensive document camera. It's a very good for the money document camera, but it'd be cool if it had like, you know, like how like fancy cars have like set seat settings, like you push the button and it goes to like the seat that you want. I wish I had a document camera that did like, I push the button and like it goes to the setting I want. That'd be great. I bet I would imagine they make that, but I don't actually know. So, oh well, I don't have it. I will just deal with the manual adjustment. So let's look at this function. F of x equal to x to the 2/5 on the interval from -1 to 32. And I want to find the absolute extrema. To find the absolute extrema. Okay, so first I'm going to find the critical values. I'm going to take my derivative, f prime of x, which is equal to 2/5 x to the -3/5. And I am going to write this as 2 over 5x to the 3/5. And I'll point out that setting this derivative equal to 0 has no solutions. This fraction is never equal to 0, because for a fraction to be equal to 0, the numerator has to be able to be equal to 0, but the numerator is always 2. So this has no solutions. However, if we set this to be, or if we're looking for where this does not exist, then x equal to 0 is going to be the critical point where the derivative is undefined. I will point out that x equals 0 is definitely in the domain of the original function. Y equals x to the 2/5 is defined for every real number x. We just have a function that's not differentiable at x equal to 0. I think it looks something kind of like, actually, let me not draw, I won't draw it yet, because we don't need to draw it to find the answers, but I will draw it in a second. So I've got my critical point, my only critical point, x equal to 0. And if I look at my function, I've got -1 to 32. So I want to find f of 0, f of -1, and f of 32. F of 0 is easy. 0 to a positive power is always 0. I do emphasize positive there because 0 to a negative power is undefined. Right? Think of 0 to the -2nd. It's like 1 over 0 squared, which is 1 over 0, which is undefined. So 0 to a positive power is 0. 0 to a negative power is undefined. F of -1 is going to be -1 to the 2/5. You can kind of go in either order you want. You can either say -1 squared is 1, and then the 5th root of 1 is 1. Or you could have said the fifth root of -1 is -1, and then -1 squared is 1. Either way, you're getting 1. When it's something easy like -1 or 1, it doesn't really matter which order you do it in. When it's something like 32, the order really does matter. Sure, you could say that 32 squared is 1,024, and the fifth root of 1,024 is 4. But we probably don't actually know that generally. And I'm really not actually doing that in my head. What I'm actually doing is saying, I know the answer is 4 already, because I know that the fifth root of 32 is 2, and 2 squared is equal to 4. Someone asked, from the 2 over 5x to the 3 halves, how did you get 0, no solution, and does not exist, x equals 0? So if I set this equal to 0, set 2 over 5x to the 3/5 equal to 0, I could multiply both sides by the denominator. And if I do that, I get 2 over 5x to the 3/5 times 5x to the 3/5 equal to 0 times 5x to the 3/5. On the left-hand side, the 5x to the 3/5 cancel out, and I get 2. On the right-hand side, 0 times anything is 0. 2 equals 0, no dice. No solution there. I don't have any values of x that are solutions to this fraction equal to 0. The shortcut way of seeing that is saying, oh, I know that if a fraction is going to be equal to 0, the numerator has to be able to be equal to 0. But 2 is not 0, so it's never equal to 0. On the other hand, if I'm setting this to, if I'm seeing where or for what values of x, where does 2 over, I don't know why underline does there, sorry. Where does 2 over 5x to the 3/5 not exist? Well, x equal to 0, because I'm looking where the denominator is 0. If I set 2 over 5 times 0 to the 3/5, 0 to a positive power is 0, and 2 over 5 times 0 is 2 over 0. Oh, that doesn't exist. We can't divide by 0. So that's how I'm getting that. It's not super duper important that you know that you're getting 0 because it doesn't exist versus because it's equal to 0, but it is something you should be aware of. You're right, and then I plugged in 0 because 0 was my only critical point, actually. And I plugged in my other 2 critical points because that's how we tip, or my other 2 endpoints, because that's how we do. Sometimes people do call the endpoints critical points. It's not really technically correct, but in the context of the problem, it's fine to say that. So here we would say our absolute maximum is 4 occurring at x equal to 32, and our absolute minimum is 0 occurring at x equal to 0. Graphically, this function looks kind of like my bird function. It's going to be, so I now have the point -1, 1, and then the point 32, comma 2. So it's going to be very like sharp here. Like, ooh, like that. So you got -1, 1, you got 0, 0, and you've got 32, comma 4. So you go, yeah, there's your max, there's your min. Function is totally defined at 0, but not differentiable at 0. Oh, something just did something. I accidentally pressed the button. Sorry. Okay, there we go. Okay. Let's talk a little bit more about the mean value. So the mean value theorem says, oh, sorry, 1 second here. So reminder, let me not lose, I always have the papers getting out of order here every time. There's never enough room on the table. Okay, so mean value theorem once again says the following. Let me say it the right way. Yeah. So if f of x is continuous on the closed interval at least, and differentiable on the open interval at least, often you have more than that, then there exists at least one, but possibly many, least one number C between A and B such that, and the way you should really read this next part is the slope of the tangent line at C is equal to the slope of the secant line between the two endpoints. Slope of the tangent, slope of the secant. And the drawing we often kind of draw to exemplify this is from sum A to sum B. Maybe the function is doing, I don't know, something like this. And so, sorry, I overshot my B. I think that might be. And so then what we're saying is somewhere between A and B, there is at least one point where the slope of the tangent line is the same as the slope of the secant line that I'm about to draw. So there's the secant line. And then it looks like there's actually probably 2 points in between A and B. One about right, I would say there. And one about right, I don't know, maybe right about there. Again, it's not precise, that's not the point. All right, but there are my 2 C values. And the mean value theorem just says that there's at least one C between A and B, so that the derivative at that point C is equal to the slope between f of A, comma f of A and B, comma f of B. So, big picture, the mean value theorem is super important. Like it comes up a lot. It comes up when you're like proving some things about increasing, decreasing. It definitely comes up in 21B when we prove that like the integral is equal to what it's equal to, like the fundamental theorem of calculus. The mean value theorem definitely plays a crucial role in that proof. But aside from that, there's not a whole lot we can really do with it as far as like asking interesting math questions. So let me give you like 1 or 2 examples and then we'll kind of move on. So here is the example of type of mean value theorem question that frequently gets asked. So we're going to say, we're going to find all values of C guaranteed by the mean value theorem for the following function, f of x equal to x cubed minus x on the following interval, from 0 to 4. So all that's being said here is that for this function, x cubed minus x, on the interval from 0 to 4, in fact, let me draw it a little bit here. So x cubed minus x definitely has an x-intercept at 0 and at 1 and at -1. If I plugged in 4, I would get 64 minus 4, which is 60, which is pretty big, right? So I don't know exactly what my function looks like, but I know it's a cubic function. And I know that it had at this point, if I plugged in 2, I'd get like 6. If I plugged in 3, I'd get something like 24. So doing something like this. And so what we're saying is somewhere, at least one place between 0 and 4, there is a point so that the slope of the tangent line is equal to the slope of this secant line. And that slope is exactly equal to f of 4 minus f of 0 all over 4 minus 0. Which ends up being f of 4 is 64 minus 4, or 4 cubed minus 4, which is minus 0 all over 4 minus 0, which ends up being 60 over 4, which is 15. So the mean value theorem says there's at least one place between 0 and 4. There could be more, where the derivative of the function is equal to 15. And this question is asking us to find that point, or those points. So we want to find all solutions. I'm going to leave myself a little bit space, over here because I'm going to write something there afterwards. Find all solutions to the equation f prime of x equal to 15. Great. So f prime of x is 3x squared minus 1 equal to 15. I'm going to add 1 over there. So that 3x squared equals 16. I'm going to divide both sides by 3. So that x squared equals 16 thirds. And what are my two solutions to this equation? Or what am I looking for really? A plus or minus the square root of 16 over the square root of 3, which I would write as plus or minus 4 root 3 over 3. Now, are both of those values that are guaranteed by the mean value theorem? The answer is actually no, because one of them isn't in the interval it's supposed to be in. So the mean value theorem guarantees at least one solution, possibly more, but the solutions it guarantees have to be between, in this case, 0 and 4. The negative one certainly isn't. So we have to find all solutions in the interval to this derivative. So the only one that qualifies here is c equal to the positive 4 root 3 over 3. The other solution, x equal to negative 4 root 3 over 3, is not in the interval, and thus not guaranteed by the mean value theorem. So if someone asks you a question like this, they often will set it up like this so that you did I make a mistake? No. Oh, I really did. That's all right. I mean, I didn't make a mistake. I used a different function, which is totally fine. Yeah, interesting. Cool. Yeah, okay. Yeah, that's totally fine. Right. Often they'll ask a question like this where you get more than one solution, but you have to exclude some of them because they're not in the interval that we're talking about. Yeah, sure. I don't love any of those questions, really. Let's look at a couple more things here. So what about this next question? What if I said my function was f of x equal to 2x plus 1 when x is less than 3 and 3x minus 2 when x is greater than or equal to 3, and we're on the interval from 1 to 4. Does the mean value theorem apply? So I'm still asking the same sort of question, like find the value C guaranteed by the mean value theorem if the mean value theorem can be applied. But the question we're asking is, does the mean value theorem apply here? So have we met all the criteria for the mean value theorem, which is that the function has to be continuous and differentiable? Well, let's check out continuity. So where might we be concerned about continuity? Right, when x is 3. So let's see, if we plug in 3 to each piece here, what do we get? So the so I'm going to use some abbreviated notation here. Like if we look at f of 3 from the left, that would be 2 times 3 plus 1, which would be 7. Look at f of 3 from the right, we're getting 3 times 3 minus 2, which is also 7. So at least it looks like continuity is okay, because if you approach 3 from the left or 3 from the right, both y values are approaching 7. What about differentiability? Well, if we look at the derivative, f prime of x would be 2 when x is less than 3 and 3 when x is bigger than 3. And I am excluding the equal to part then, because we only get to include the equal to part if they actually match up. So here, the left derivative and the right derivative aren't matching up. Graphically, what's happening is 1, 2, 3, 4. We plug in 1, we get 3. We plug in 3, we get 7. If we plug in 4, we get 12 minus 2, which is 10. And so our graph kind of looks like this. I should make that point a little higher. Right, we've got different slopes on the left and the right of 3. That function has a corner. It's clearly not differentiable. So the mean value theorem does not apply because f of x is not differentiable on the entire open interval from 1 to 4, specifically at x equal to 3. So often a piecewise function will fail to meet the criteria of the mean value theorem, either by failing to be continuous or by failing to be differentiable. But it doesn't have to fail. For example, we could be given this other function, which is going to be perfectly fine. F of x equal to x squared when x is less than 3, equal to 6x minus 9 when x is bigger than or equal to 3, and we're still on the same interval from 1 to 4. Before you even worry about differentiability, we should make sure continuity is a check. So are we continuous at 3? Let's check. F of 3 from the left would be 3 squared, which is 9. F of 3 from the right would be 6 times 3 minus 9, which is 18 minus 9, which is also 9. How about differentiable at x equal to 3? Well, my derivative is looking like 2x when x is less than 3 and 6 when x is bigger than 3. But we can see that from the left side, as x approaches 3, the derivative when we get closer and closer to 3 is going to be 6 on the left, because you plug in 3, and 6 on the right. So we can go ahead and include the equal sign here, and we're actually getting that the slopes are matching up. So unlike the previous one, where you have a slope, a sharp slope change, here the graph looks something like, and it doesn't have to be perfect, it looks something like we've got x squared from 0 to 3. So from here to there, you've got like your usual parabola kind of deal. And then from 3 onward, the slope exactly matches up and it's just a straight line like that. But there's definitely no jarring change there. Yeah, I mean, it's a big number there. So great, that means the mean value theorem applies because we have continuity, we have differentiability. So if I want to find the C guaranteed by the mean value theorem, well, first I need to find f of b minus f of a over b minus a. So f of 4 minus f of 1 over 4 minus 1 is going to be, let's see, f of 4 is going to be 6 times 4 minus 9. Minus f of 1 is going to be 1 squared over 4 minus 1 is going to be 24 minus 9 minus 1 over 3. That's 14 over 3, which is 14 over 3. So then you have to take the derivative and set it equal to 14/3. So let me ask you, it can't be, well, let me tell you, it can't be in this part where x is bigger than 3. So when x is bigger than 3, the derivative is just 6. So it has to be setting this part equal, this derivative of this part equal to 14/3. So we're going to set f prime equal to 2x equal to 14/3, which means we're going to get x equal to 1/2 times 14/3, which is 7/3, which is certainly in between x equal to 1 and x equal to 3. So we're okay. And I did say 3 on purpose there because I know I have to be less than 3 for it to be using this part. So kind of funky, but people definitely do. People try to make up questions around the mean value theorem because it's such an important theorem. They want you to have some exposure to it. And these are the kinds of questions we often come up with. Okay. Last thing we'll say about these theorems, at least directly, is, and this problem is kind of in a similar vein as to the that weird problem on Grobner's practice midterm where it was like talk about how many solutions this equation has, and it was like you had to use like cosine was bigger than 1 and all that kind of, so this problem is in a similar-ish vein but a bit more straightforward. So we're going to show that f of x equal to x cubed plus x plus 1 equal to 0 has exactly one solution. In the interval from -1 to 0. So when you're asked to show something has exactly one solution, The name of this process is typically referred to as an existence and uniqueness proof. So there's two parts to it. The first part is proving the existence. And then the second part is proving that it's unique, meaning it's the only one. And this is, if anyone's a math major, this is a pretty common thing that comes up frequently, right? Where you first show that something exists and then show that it's the only one. So let's do the existence part first. Normally, or at least in the past, we have shown that a solution to an equation exists by using the intermediate value theorem. So that's what we're going to do first. So we're going to say that we're going to do the existence part. So first of all, I would note that f of x is continuous everywhere, which is a requirement for, which it has to be continuous on the interval for the intermediate value theorem to apply. And the second part is that f of 0 is 0 plus 1, which is positive. And f of -1 is -1 plus -1 plus 1, which is -1, which is negative. So by the intermediate value theorem, since the function is continuous and it goes from a negative number to a positive number, it has to equal 0 somewhere in between those two x values. So by the intermediate value theorem, there is a number c between 0 and 1, sorry, between -1 and 0, such that f of c was equal to 0. Great. Okay. Now the uniqueness part. So most of the time when you're trying to show that something is unique, you do so by assuming that it's not. Say we're going to assume that there are two solutions to this, and then we're going to derive some sort of logical impossibility. So we're going to assume that A and B are solutions to f of x equal to 0. Meaning f of A is equal to 0 and f of B is also equal to 0. But look, so we have a function that's continuous and differentiable everywhere, right? Certainly this polynomial, that's like the best thing about polynomials is they're, well, it's not the best. It's one of the best things about polynomials. They're continuous everywhere. They're differentiable everywhere. So this function is certainly continuous and differentiable between A and B. So here's what I've got. I've got that f of A equals 0 and f of B equals 0. And I've got some function doing something between them. Maybe it looks like that, maybe it looks different. But here's what we can say. Rolle's theorem, the special case of the mean value theorem, since my function is continuous and differentiable, since f of x is continuous and differentiable on the interval from A to B, and we just said that f of A is equal to f of B, then by Rolle's theorem, there has to be a number between A and B where the derivative is equal to 0. There is a number between A and B. Let's call it C. Sure, let's call it D. Such that f prime of D is equal to 0. And here's where we're going to run into a problem. We take the derivative of our function. F prime of x is equal to 3x squared plus 1. And that function is never equal to 0 for any value of x, unless you, well, I should say for any real value of x. So this is not equal to 0 for all values of x. But that means we've run into a logical impossibility. Our assumption and Rolle's theorem together say that there should be a solution to this equation, but the math obviously shows that there should not be a solution to this equation. So that means the thing that we assumed was true, that there were two solutions, is wrong. Because if it was true, then we'd have this thing that should be true, but it's not. So our assumption is false. Meaning there is only one solution. to f of x equals 0. That's, again, kind of in the same vein as that Grosvenor problem from last class, but a little bit different. This is something people occasionally like to ask about, but if you haven't gone over it in class, it's probably not going to show up. Okay. So let's move along. So those are kind of all the theorems at play when we start talking about graphing things. So graph it. Or people would often call it like detailed sketching, detailed graphing, whatever you want to call it. So something important that we need to know, although we've certainly been using this fact for a while, is that is that f of x is increasing if and only if f prime of x is positive. So a function is increasing is equivalent to saying its derivative is positive. Similarly, f of x is decreasing is equivalent to saying, or if and only if, f prime of x is negative. So a function is decreasing exactly when its derivative is 0, and a function's derivative is 0 exactly when it's decreasing. Just as a point of interest, your teacher might have said if and only if and written IFF. That's what they mean when they write if with 2 F's, is that if and only, meaning that both directions imply each other. This statement says if f of x is decreasing, then f prime of x is negative, and vice versa. If f prime of x is negative, then f of x is decreasing. That's what an if and only if statement means, or a bidirectional implication. Okay. We use that fact a lot. So let's go ahead and, let's graph f of x equal to x to the 4th minus 4x cubed. And so here's what I'm going to typically say when we graph something. So when I say graph something, this is going to mean find the following: the y-intercept, the x-intercepts, any vertical asymptotes, any horizontal asymptotes. What I often call the first derivative stuff, which is the relative extrema, and where the function is increasing or decreasing. And then we're not going to do it here because we haven't talked about it yet, but we're also going to do the second derivative stuff, which is any inflection points and where the function's concave up or concave down. And we'll get to concavity, but for this first one, we won't talk about it because it's not super duper important. So for this function, the y-intercept is not a big deal, right? If I want to find the y-intercept, I'm going to set x equal to 0. I'm going to get y equal to f of 0, which is 0 minus 0, which is 0. Y-intercept is usually not too bad to find. X-intercepts, plural, typically. Although you don't have to be, right? Some functions don't have any y-intercepts or any x-intercepts, but this is the process for finding them. We're going to set we're going to set y equal to 0, or your function equal to 0. So we're going to get x to the 4th minus 4x cubed equal to 0. We're going to solve this by factoring. We're going to have x cubed times x minus 4 equal to 0. And we're going to get either x equal to 0, which we already knew was going to be an intercept because y equal to 0 was an intercept, or x equal to 4. Cool. After that, we would usually look at the asymptotes, but for any polynomial, which this is, we're never going to have asymptotes. No vertical asymptotes, no horizontal asymptotes. So if you see something in the polynomial, move on. If it's a rational function, a polynomial divided by polynomial, typically you have vertical and horizontal asymptotes, or at least you have a very good chance of having them. So now we're going to move on to what I always refer to as the first derivative stuff. And we're going to start by just finding the critical points. So find the critical points. So I'm going to take my derivative, which is 4x cubed minus 12x squared. And I'm going to see where it's either equal to 0 or undefined. We don't need to look for the undefined part here because it's, again, a polynomial, and a polynomial is never undefined. So if you know something's not going to be undefined, don't be like, oh, where is it undefined? You need to be like, I know it's not undefined. So that's equal to 0. And again, we're going to factor as much as possible. I'm going to pull out a 4x squared, left with an x minus 3. So I either get x equal to 0 or x equal to 3. And then the usual thing we do after we find our critical points is we put them on the number line. And we ask ourselves what the sign of the first derivative is. So I'm just going to pick a point larger than 3, like 6, and plug it in. 4 times 6 squared times 6 minus 3 is a positive times a positive, which is positive. And then you can keep picking, like you could pick x equal to 1. 1 squared is positive, 1 minus 3 is negative, so a positive times a negative is negative. Or you could have said, well, the 3 came from that factor has an odd power, so the sign's going to change. Similarly, 0 came from that factor, which is with an even power, the sign's going to stay the same. Or you could have plugged in -1, and -1 squared is positive, and -1 minus 3 is negative, and a positive times a negative is a negative. And then after that, we then say, oh, wait, we know a thing. If the derivative is positive, the function's increasing. The derivative is negative, the function is decreasing. If the derivative is negative, the function is decreasing. So we know the shape of the function now. We know it's decreasing, and then still decreasing, and then increasing. We also know where we have relative extrema. And again, we'll write this down in a minute, but the first derivative test tells us that if you have a critical point and the function is decreasing on the left and increasing on the right, you're bottoming out. You have a relative minimum there. So we definitely have a relative minimum at x equal to 3 because f prime goes from negative to positive from left to right. We're always saying from left to right. It's always from left to right. There is no right to left. At least not in math. There are certainly. There are some languages that are right to left, which just seems really interesting to me. Like it just feels like it'd be very counterintuitive from my perspective, but obviously not from other people's perspective. On the other hand, we don't have, so at 3 we have a relative minimum. We don't have anything at 0. So x equal to 0 is neither a minimum nor a maximum. Because it's decreasing. I guess we should go ahead and talk about the second derivative stuff as well. And then we'll codify this in a second, but let's go ahead and just fill it in. So let's do the second derivative stuff. Before, one more thing. So sometimes people also like to ask about where a function's increasing or decreasing. I usually find that silly to write because I can tell you right now, looking at the sign chart, it's decreasing from -infinity all the way up to 3, and it's increasing from 3 to infinity. But sometimes people like to ask that question. So there you go. Let's go ahead and look at the second derivative stuff. When I say second derivative stuff, what I really mean is we're going to kind of do the same thing we just did for the first derivative. We're going to take the second derivative. We're going to set it equal to 0 to find the critical points for the second derivative. And then we're going to talk about what the sign of the second derivative is everywhere. So my second derivative is going to be, so looking back at my first derivative, a good thing to do is I wouldn't take the derivative of the factored form. I don't want to use the product rule if I don't have to. I would much rather take the derivative of the unfactored form. So the derivative of 4x cubed is 12x squared. The derivative of 12x squared is minus 24x. Setting that equal to 0, we again factor out the 12x and left with an x minus 2. set that equal to 0, and then you're either going to get x equal to 0 or x equal to 2. I'm looking at the sign chart for that. You do the same sort of thing. You pick a number larger than 2, like 3, plug it in, and it's positive, positive, so the whole thing's positive. And then for each of these, since the power is odd, you're going to change signs every time. So I picked 1, you'd have a positive times a negative. You pick -1, you'd have a negative times a negative, which means that our function is, and we'll talk more about this in a minute, concave up left of 0, concave down between 0 and 2, concave up right of 2. So if someone asked you where this function was concave up or down, you would say it was concave up on the interval from -infinity to 0, union 2 to infinity, sorry about that, and concave down from 0 to 2. And since we're already there, might as well just say it. That means that we're going to have inflection points at 0 and at 2, because you get an inflection point. I'll say there's slightly more to what I'm saying than what I'm actually saying, but very generally, you get an inflection point where the function is continuous and differentiable, and the second derivative changes signs. So we get an inflection point at x equal to 0 and x equal to 2. Now, if I was really trying to graph this nicely, for each important point I found, intercepts, critical point, or extrema, and inflection points, I would also find the corresponding y value. So looking back at the previous page for a second, for my relative minimum of x equal to 3, I should plug that into the original function to find the y value. It's going to be kind of gross. So my function, which was x to the 4th minus 4x cubed, I really don't want to calculate 3 to the 4th minus 4 times 3 cubed. And I shouldn't. I should first factor before I try to plug in a number. So I rewrite this as x to the 3rd times x minus 4. It's a little bit easier to plug in 3. F of 3 is going to be 3 cubed times 3 minus 4, which is 27 times -1. Similarly, to find the y value of this inflection point, f of 2 is going to be 2 cubed times 2 minus 4, which is 8 times -2, which is -16. I don't need to plug in the 0 because I already plugged in 0 to the function to find the y-intercept, which is also 0. So typically when we're graphing these things, we're trying to graph all the details, we find the y values of your critical points, of your relative extrema and of your inflection points. Cool. So now I'm going to graph this thing. I'm going to plot all the things I can. I'm going to plot 0, 0. I know my other intercept was 4, 0. And I would say when I graph things like this, my x-axis is kind of spread out. My y-axis is kind of compressed, meaning, right, this much distance here is going to like 4 or 5 worth of x, whereas this much distance here is going to be like 30 worth of y, and that's fine. So I know I'm going to have a relative minimum at 3, -27. So over here at 3, I'm going to get like my minimum. And really, that's all I want. I don't want to actually plot my inflection point just yet. I'll get there when I get there. When I graph this, you know what I'm using to graph it? I'm using my first derivative sign chart. I know that my function, so I even maybe I lined this up pretty well. Look at that. So here's 0, there's 3. And what's happening is from left to right, I'm decreasing until I get to 0. I'm decreasing again until I get to 3, then increasing after that. I know I also have an inflection point at 0, 0. So I know I should be concave up, flatten out because the derivative is 0 there, and then concave down, and then I change concavity and concave up. Not too shabby. Okay. So that's kind of the basics of graphing a function, including as all the details we can. Again, this one didn't have any vertical or horizontal asymptotes, but still, that notwithstanding, we've kind of seen it. let's say a few things about relative extrema and inflection points so that we're more clear about how we find those. So for relative extrema, we have what's called the first derivative test. Relative extrema, also called local extrema, depending on people go back and forth. Like people are going to say, your teachers are going to say both of them probably. I don't think I've ever met anyone who purely says local or purely says, it's just like, yeah, we call them both things. For relative extrema, we have this thing called the first derivative test, which is basically what we just said. I'm going to say all the words before I write down the thing. So the basically says if you have a critical point and your function goes left to right, increasing to decreasing, then you're increasing and then decreasing, so you have a relative maximum. On the other hand, if you go from decreasing to increasing, you have a relative minimum. And if you have anything else, like increasing, or decreasing, you don't have a relative extreme. So first derivative test says, and I should try to write this out in a very, I feel like I write this out in a very ad hoc way that is not super great. And do I have my notes on here? No, I don't. 1 second. Sorry. I just feel like I really like to give you the actual kind of nicer version of this. One moment. And I just said one moment again. Let's look at the book. It's good to look at the book. Sure. Yeah, there we go. Okay. Interesting. Or maybe I won't look at the book. I thought it was here. Sorry. I've clearly hidden the books. I was looking for the book, a different book. Oh, there we go. There it is right there. Cool. Awesome. So. Sorry. Oh my God. Sorry. I feel bad for being not as prepared as I should be because I should definitely have this already, but take a break, have a sip of water while I find this thing. One second. I keep saying 1 second like it's going to be any faster. Let me just stop talking. Cool. Page 237. All right, here we go. Finally, it only took me forever. They give some nice pictures. So your book is, I mean, I will point out the book is nice. Like it's like the book has nice pictures. It is actually worth looking at. You have paid, or someone has paid some amount of money for you to have access to the book. It is nice to look at. There are good pictures in there, if nothing else. So here's what the first derivative test says for local extrema. Suppose that C is a critical point of a continuous function f that is differentiable at every point in some interval containing C, except for maybe at C itself. So you might be thinking of a picture like this, where your interval, right? You have something that maxes out like that, and there's your C. That function is continuous on some interval containing C and differentiable everywhere around C and also at C, right? This one's totally differentiable at C the way I've drawn it. But it could also look something like this. where the function is continuous everywhere around C and differentiable on an interval containing C, except for at C, right? Because again, we've classified critical points as points where the derivative is either equal to 0 or the derivative doesn't exist. And those critical points are candidates for relative maxima and relative minima. So now, yeah, I feel like the way they've written this is, I mean, it actually, I like it. So moving from left to right, or sorry, moving across this interval from left to right, three things can happen. One, if the derivative goes from positive to negative, so if f prime changes from positive to negative, then we have what? By the way, this is why the picture is better. Because I'm like, okay, well, I'm like, if we go from positive to negative, that means we're going from increasing to decreasing. So we have a relative maximum. And we're going up, but then down. So we have a relative or local maximum. Or if f prime changes from negative to positive as we go from left to right, then we have a relative minimum. Idea, right? We have something that looks like this. There's your C. You're going down and then up. Negative, positive. And then finally, if the derivative doesn't change signs. So if it goes positive, positive, or negative, negative, then we do not have a local extrema. And I will add on to this. If you have a critical point of your first derivative and you don't end up having a local extrema there, it is often, not always, the case that you end up having an inflection point at that. Kind of like we did in the previous example, actually. Right? We had a critical point at 0, but the derivative was negative on both sides of it. But then that 0 ended up being an inflection point. So that doesn't always happen, but it often happens. Cool. So we're not going to prove it. So again, I don't think you should actually, like, I clearly don't know the words of this definition by heart. And you shouldn't. What you should really know is the picture, right? If you have this kind of situation where it's positive, negative from left to right, you have a relative max because you're thinking, oh yeah, increasing, decreasing. Or if you go from negative to positive for your first derivative, that means you have a relative minimum. Ooh, yeah, so let's yeah, we'll do something fun here. So let's say we have the following function. Let's say we have, yeah, let's do that. So I want to make sure it comes out okay. Let's say we have f of x equal to, yeah, let's say x. Is x gonna be all right? Sure, why not? X over x minus 1 squared. And we're gonna find, we're not gonna deal with the inflection points for this one yet, but we will deal with the other stuff. So let's find the usual things. So first things first, my y-intercept gonna be f of 0 is gonna be 0 over 0 minus 1 squared, which is gonna be 0. X-intercepts, set the whole thing equal to 0. But when you set a fraction equal to 0, you're just setting the top equal to 0, and that's going to be x equal to 0. So we just get x equal to 0. Vertical asymptote, or totes, set the denominator equal to 0. Set x minus 1 squared equal to 0, and you end up getting x equal to 1. Horizontal asymptotes for a rational function like this, you have to compare the degree on top with the degree on the bottom. What is the degree on top? X to the, was the term is X, but the power is 1. What's what's the degree on the bottom? Right. So when I say degree, the answer we're looking for is just the number. So yeah, the degree on the bottom is 2. And so since the degree on top is less than the degree on the bottom, the horizontal asymptote is going to be y equal to 0. Now, really, the work we're not doing here is actually taking the limit as x goes to infinity. If you wanted to do that, you could say the limit as x goes to infinity of x over, if you want to multiply at the bottom, say you have x squared minus 2x plus 1, that is going to be 0. And you can find that by dividing the top and bottom by x squared, and then see you have a 1 over x on top, which goes to 0, and a 1 minus 2 over x plus 1 over x squared on the bottom, which goes to 1, and 0 over 1 is 0. But usually we just use the shortcut because there's so many other moving pieces to these graphing problems that you don't want to spend so much time doing that. There are some other graphs we will encounter where we actually do have to use the limits. Oh, that reminds me. We haven't talked about L'Hopital's rule yet, right? Yeah. It's usually like there are some graphs we often have to use L'Hopital's rule for to find limit, but we're not quite there yet. All right, we've done all of my pre-first derivative stuff. Let's do the first derivative stuff. The first derivative. Okay, so I'm gonna, okay, quotient rule. Bottom times the derivative of the top minus the top times the derivative of the bottom, which is 2 times x minus 1 to the first times the derivative of x minus 1, which is just 1. I'm really trying to cover my chain rule basis there. It's really cold in here. Maybe I'm standing too close to the window. It's a little chilly over here. The denominator is x minus 1 squared, which is x minus 1 to the fourth. So this is where we actually do have to simplify this to be able to find the solutions. And typically when you have a quotient rule kind of thing, if your denominator started off as being raised to a higher power, usually you can factor out some amount of whatever is being raised to a power. Meaning in the numerator, I should be able to factor out at least an x minus 1 to the first, maybe even to a higher power. Here it is just to the first. I have an x minus 1 squared here. I have an x minus 1 to the first here. So I'm going to factor out an x minus 1 to the first. Let's see if I can. That's better there. Okay. So factoring out an x minus 1 from the top, I'm left with an x minus 1 still there, times 1, okay, minus an x times 2 times that goes away, times 1, so a 2x over x minus 1 to the 4th. I can cancel one of the x minus 1s. And then I'm left with, if I simplify the top, x minus 1 minus 2x, well, x minus 2x is negative x minus 1 over x minus 1 cubed. Be careful here. It's really, really tempting to try and cancel another x minus 1, but I don't have x minus 1 on top. I have negative x minus 1, or if you prefer to factor out a minus 1, negative 1 times x plus 1. And that doesn't lead to any canceling of any sort. If we set this equal to 0, what do we get for x? Ooh, good question. Is it gonna, okay, so there's two possible answers. One of them's right, one of them's wrong. If I just set this equal to 0, I'm ignoring the other part for a moment. The answer is either x equal to negative 1 or x equal to positive 1. Which value of x makes this fraction equal to 0? Yeah, it's the negative 1. Because that's where you're getting the 0 in the numerator. So if you plug in negative 1, you get negative 1 plus 1, which is 0, over negative 1 minus 1, which is negative 2 cubed. So you have like 0 over negative 8, which is 0. So if you set this equal to 0, you get x equal to negative 1. But then if you see where this is undefined, you get the other value, which is x equal to 1. So usually here, you can be kind of loosey-goosey, which is a terrible thing to say. I feel like such an old person saying loosey-goosey. You can be kind of less safe with your choices as far as if you're looking for 0 undefined. But don't be too uncareful. And here's why. So if I then throw the number line at this, okay, putting both those values on my number line, negative 1 and 1. So if I pick a number bigger than 1, also this is why it's really good to factor it completely. Yeah, let me say more here. You should factor this completely, and you shouldn't like bring anything over to the other side when you're trying to solve this. You want to keep the 0 on the other side by itself because you have to then plug things back in to determine whether your derivative is positive or negative. So you really want, oh yeah, this is my derivative. And I want to plug in, say, x equal to 2 and find the top is a -1 times a positive, and the bottom is positive, so the whole thing's negative overall. And then if I pick a number between -1 and 1, like 0, -1 times 1 is positive. The denominator is a negative number cubed. Positive over, wait, negative on top, negative on bottom, positive overall. Or what I should have really done is followed my own advice and said the 1 came from the x minus 1. It's raised to an odd power, so the sign changes. The -1 came from the x plus 1. It's raised to an odd power, so the sign changes. All right, I'm about to try and trick you, just so you're aware. You might get tricked, it's okay. So at x equal to -1, I should say, right, our function is going decreasing, increasing, decreasing. So at x equal to -1, we have what? Relative max or relative min? This isn't the trick, right? But even if it is the trick, lean into it. We have a relative minimum. Or if you know the trick, then tell me why I'm tricking you. At x equal to +1, we're increasing, decreasing. We have, right, and so that's where the trick is, because we don't have a maximum there, because we have a vertical asymptote at x equal to 1. So if you look back at our work here, we have a vertical asymptote at x equal to 1. So here's what's really happening. At x equal to 1, right, it goes up, down, 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 but no maximum because it's undefined there. So let's back up a little bit here. Right here, x equal to 1 isn't a true critical value or a true critical point. It's what I call a pseudo-critical point. It's still important to include in the sign chart because you definitely want to know that the function goes from increasing to decreasing when you go from the left of 1 to the right of 1. But we know we don't have a critical value, or I should say, we know we don't have a relative extrema there because we know that the function is undefined there. Because if you look back at the definition of relative extrema, it said, suppose that C is a critical point of a continuous function f. This function is not continuous at that point, so it can't be a critical point. So that's what I wanted to say. I mean, it's fine to see that the first time, but don't get fooled by that in the future because people will try to fool you that way. They're like, oh yeah, look, increasing, decreasing. No, it's not a critical point. We have a vertical asymptote there. I often, when I draw this number line for numbers where the function's undefined, I like to draw little open circles there. Like, oh yeah, you don't get to exist there. Now, to be further, that's not to say that the derivative being undefined means the function doesn't exist there. We've already seen examples like the x to the 2/5 one, where the derivative was undefined and you still had an actual relative minimum there. So the name of the game really is be careful. So here we have nothing. I mean, that's not true. We actually have a vertical asymptote. But if you have a vertical asymptote at some x value, you can't really have anything else there. You can't have a relative max, you can't have a relative min, you can't have an inflection point because it's literally undefined there. Okay, so then graphically, graphically, we definitely don't want to think about finding the terrible second derivative in the inflection points, but we have, we should find the y value at -1. So f of -1 is going to be -1 over -1 minus 1 squared, which is -1 over 4. So now let's try and graph this thing. I'm just going to put all my pieces of information on my graph. I have an intercept at 0, the origin. I have a vertical asymptote at x equal to +1. I have a horizontal asymptote at y equal to 0, which I'm not going to draw because it's just the x-axis. And I have a relative minimum at x equal to -1, y equal to -1/4. And so then looking at my first derivative sign chart, I know left of here, the function is decreasing. Right of that point, I'm increasing until I get to 1, and then after 1, I'm decreasing. Also, importantly, when I'm decreasing here, watch this for a second, I can't come down like this. Because I can't cross the x-axis anywhere over here because I don't have any x-intercepts over here. So the only thing I can really do is I can do like this. That's the only option I really have. Because I can't cross the x-axis and I also have the x-axis as a horizontal asymptote. And then after -1, I'm going to increase, hit that point, keep increasing, vertical asymptote up, 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 up. On the other side, still have a vertical asymptote, but it can't be down here because I'm not increasing. I have to be up here so I can start high and then decrease afterwards. If you were to find the second derivative, I would point out that it looks like over here it's concave up. And then somewhere here the concavity changes and it's kind of like over here it's concave up and over here it's concave down. A couple ways, in fact, actually, we'll say that now. How much time have we got? I have enough time. So let's talk about concavity just for a minute, because concavity is kind of interesting, I think. So, concavity. I know we haven't formally defined it yet, but this function is for sure concave up. It is opening upwards. So if this is my function, f of x is for sure concave up. We're opening upwards. Okay, well, let's talk about what that means as far as the derivatives of this function. So if I start drawing some tangent lines, if I go from left to right, I point out that the slope of my tangent line is increasing. My tangent line has a very can you guys see that okay? I feel like I didn't draw that very well. My tangent line over here has a very negative slope. My tangent line here has a less negative slope. My tangent line here has a less negative slope. My tangent line here has a 0 slope. And then my tangent line over here has a slightly positive slope. And then a more positive slope. And a more positive slope. So if you from left to right are really negative, so really negative, less negative, 0, slightly positive, positive, more positive, you are increasing. So if a function is, or I should say, not sorry, the derivative, right? That's what we're talking about. The derivative, the slope of the tangent line, the derivative is increasing. Okay, now I know I've said this a few times. Don't look at the paper for a second. We know that if a function is increasing, its derivative is positive, right? If the function is increasing, its derivative, its slope of the tangent line is positive. So if a function is increasing, its derivative, what's that? Is no. So its derivative is positive. So if the function, which I'm calling f prime, is increasing, its derivative, f prime prime, is positive. So that's how we find concavity. If the second derivative is positive, the function is concave up. Similarly, if you have something that's concave down, the first derivative is decreasing from left to right. Starts off super positive, then less positive, then 0, then slightly negative, then more negative. So the first derivative is decreasing, right? The first derivative isn't necessarily negative or positive. It starts off positive, it gets less positive, and then becomes negative. But then the derivative of that function, since that function itself is decreasing, its derivative, f double prime, is negative. One of my favorite things to say is concave up like a cup, concave down, like a frown. Sounds silly, I know, but it's hard to forget. If you can see the picture, it's hard to forget. Concave up like a cup, concave down like a frown. The other thing that you might see from this picture here, which took me many years to kind of notice, is that when a function is concave up, the tangent lines are all below the function. When a function is concave down, the tangent lines are all above the function. And then when you have an inflection point, if I can draw another piece of paper here, grab. So then when you have something that has like something like that, where we go from concave down to concave up, at the inflection point, which looks like it's about right there, you have a change in concavity, and the tangent line goes through the function. So it goes from being above where it's concave down to below where it's concave up. So an inflection point is where the concavity changes. You can. And it's where the tangent line isn't always above or always below, but it literally goes through the function. Because on the side that's concave down, the tangent line is above, and on the side that's concave up, the tangent line is below. It's kind of neat.